Welcome to week 5. This is part B of this week's lesson. Today, you guys are going to be comparing the amount of work it takes in different scenarios. This week's main vocabulary word is work. What is work? Well, the scientific definition of work is not the exact same as the everyday definition of work. I want you to think of scientific definition of work to be more like physical work. For example, here's an everyday use of the word work. Right now, you're sitting here watching this video, so you might tell your parents, hey, I'm doing my work, my homework. Well, this is not physical work, right? You're just staring at a screen. So this does not meet the requirements of the scientific definition of work. So the definition of work that we're going to be using, think of more of physical work. I'm going to give you 4 scenarios right here. We're going to come back to these at the end. And I want you to figure out, are these people doing work on these objects? Okay, so the first example is this guy and a skateboard. He's walking along following the skateboard. The skateboard has been pushed and now the skateboard is coasting along next to him. So my question is this guy doing work on the skateboard? And then here is a gal who's pushing against a wall, right? And the wall is very stubborn and will not move. She's pushing very hard though. And the question is she doing work on the wall? Here's a gal who's lifting weights. Is she doing work on the weights? And here's a kid pulling a wagon. Is he doing work on the wagon? There's 2 objects in all these. So usually when we talk about doing work, we're talking about doing work on something. So we're going to come back to this. So into our notes, what allows you to do something? What allows you to do something? Well, the short answer is energy. So work, capital W, work, is measured in joules, capital J, is one way that energy is transferred from one object to another. That's what work is, when you transfer energy from one object to another. That's why we had 2 objects in each of our examples. Okay, so here's the actual equation or calculation. A joule, which is how we measure work, that equals 1 Newton times 1 meter. So a joule is a Newton meter. Remember that dot means multiplication. These are the units. Joule is a Newton meter. Newtons times meter. We know about newtons, right? That's force. We know about meters. That's distance. So somehow force and distance together are going to make a joule. So we want to get this in our notes. I'm going to turn into my notebook. I'm going to go to page 45 on my notes. All right. W is work, joules. That's the definition of work and the units. So let's use an example. So doing work, lifting a heavy water bucket out of a well is physical work. So we're going to be doing an example here of lifting a bucket out of a well. Well, that sounds like work. So let's go ahead and copy this part here. I'll zoom into that. And we're going to copy this in our notes. Two, 3, 4, 5, 6. Like 6 lines. 6 lines down and a little bit of space in between. And this bottom line has water. Okay. Now, of course, we're going to put in the middle is a bucket. Handle on it. There's an arrow up, and that's the direction we're pulling it in. Force of gravity. Some important things to remark on here. The height in meters, right? Because the more you're lifting this out of the well, the more height, the more work you're going to be doing. That makes sense. Looks like it's going from the top of the water out of the well H. That's your height in meters. And then on the side, the force of gravity down is called weight. It's in newtons. Force of gravity is m times what? It's little g. M times little g. So that's work. We're going to be doing some practice of that today. And now, something else measured in joules is energy. Energy is in joules, and it's the ability to do work. So the more energy you have, the more work you can do. And another way of measuring energy is in calories, something you may have heard of. 1 calorie equals 4,200 joules. So you can see they're kind of the same thing. Energy, joule, Alright, so there's your page notes. Work is in joules, and it's one way to transfer energy to an object. Here's an example of a bucket being pulled out of a well, and energy is also in joules. We want to go back and put these variables in our table of contents. I'm on page 45. W is joules, work, page 45. And then E is joules, energy, page 45. So before we move on, I want to ask you a question. What is the major common unit that scientists use to measure work and energy? What do we measure work and energy in? It's joules. And now we're going to do a couple examples. In order to find the amount of work done to an object, you just take the newtons times the meters. And so we're going to be doing examples right now where you lift things. So the newtons is going to be the weight of the object, and the meters is going to be how high you lift it. So let's try a couple examples. This first one, which takes more work, the most work to lift? Does it take more work to lift a 2,000 Newton elephant 1 meter high? 2,000 newtons is the weight of the elephant, and the meter high is how far you're lifting it. Or lifting a 0.2 Newton feather 5 meters high. Which of these two takes the most work to lift? So first you have to figure out the amount of work done, right? So to lift the elephant, 2,000 newtons 1 meter high is going to be 2,000 times 1 meter, which is going to be 2,000 joules. All right, and to lift the feather is going to be newtons times meters, 0.2 newtons times 5 meters, and that ends up being 1 joule. So the elephant takes way more work to lift than the feather, and that kind of makes sense. Let's try a little bit different one. Okay, here I have a feather and a bowling ball, but this time we're going to lift a 0.2 Newton feather 1,000 meters high, and this bowling ball, it's 20 Newton bowling ball, it's heavier, but we're only going to lift it 1 meter. All right, which of these two takes most work to lift? So the feather is 0.2 newtons, and you lift it 1,000 meters. 0.2 times 1,000 ends up being 200 joules. And the bowling ball is 20 newtons, and you lift it at 1 meter. 20 times 1 is 20 joules. So the feather this time took more work to lift. Okay, so I want you to notice it's not just the weight, it's also how far. Weight and distance both. Okay, so going back to our example with the bucket lifting out of the well, we want to turn this into an equation for work. Remember, the weight is something times g. The weight is something. What's the weight? Something times g. What goes here? Mass times g. Okay, and then work, we know work is force times distance. Newtons times meters, there's going to be 3 letters that go here, 3 variables. We want to figure out an equation for work using this example. Anytime we lift something, we are doing work, so we want to figure out an equation for that. So let's work on this side first. Distance. So what letter in our example here, which letters here, means distance? It's the height. So height, h, that's the distance. Now, force, there's 2 letters we got to put together to come up with the force. So how do we get the force in this situation here when we lift something? It's going to be the mass times the gravity. It's going to be the weight, which is m times g. So here is another equation. We're actually going to use this one more often. To find the work to lift something is mgh. That's the force times the distance, the weight times the height. So go back to your notes here and add work equals mg, that's the weight, times h, the height. All right, so that's it for our notes for today. So I want you to put this together. We're going to do our last review questions. In order to have work done, you have to have newtons and meters. You need to have force and distance both being done, force and distance. So something's got to be moving, and you have to be applying a force to it. So here's our 4 examples we started this video with. So which of these 4 are they doing work, and which of these 4 are they not doing work? Okay, first we'll start with the gal lifting weights. Is she doing work on the barbells? So remember, to do work, you have to have force and distance. Yes, she is doing work because the force is the weights themselves, lifting the weights, and then the distance is how far she lifts them up. So the force and distance, so she is doing work on the barbells. What about this guy? The skateboard is coasting along, and he's walking next to it and kind of just watching it. Is he doing work on the skateboard? No, he's not doing work on a skateboard because even though there's distance, the skateboard is moving forward distance, he is not putting any force on the skateboard. So he's not doing any work because there's no force. What about this boy pulling a wagon? Is he doing work to the wagon? Yes, because the wagon's moving and he's putting a force on it, force and distance, so he is doing work on the wagon. What about this gal pushing the wall? Is she doing work on the wall? No, she's not doing work on the wall. Think about it. Because even though she's got a force on the wall, she's not moving the wall. There's no distance. All right, so you can see in our examples, these 2 are not doing work. In the first case, there's no force. He's not putting a force on it. In the second case, even though there's a force, she's not moving it a distance. So you have to have force and distance both. In these 2 cases, they both have force and distance, so they're doing work.